Okay, now we have a tank that contains a mixture of helium and xenon gas at a temperature of 400 K. If the xenon atoms have a much larger mass than the helium atoms, which of the following are true? Circle all that apply. Okay, so now we're looking at a gas. So if we go and look at our ideal gas law, we know PV equals N kBT, and we know that the average kinetic energy for an ideal gas is 3/2 kBT, which is also the same as 1/2 m times the average of the velocity squared. Okay, so A says the helium atoms have a higher kinetic energy. So they don't have a higher kinetic energy because all of these, if you have a tank of two different helium atoms and they're at the same temperature, then the average kinetic energy is 3/2 kBT. So if they have the same temperature, they have to have the same average kinetic energy, which means that the average kinetic energy of the xenon atoms has to be equal to the average kinetic energy of the helium. So they have the same kinetic energy as the xenon atoms. So that one's wrong. And B is true. So how is it possible that they can have the same kinetic energy if one of them has a different mass? Well, they have the same kinetic energy 3/2 kBT, which is also equal to 1/2 times the mass times average velocity squared. So the atoms that have a larger mass just have a smaller average kinetic energy. So the xenon atoms have a higher RMS squared velocity than the helium atoms. Okay, so the xenon atoms have the bigger mass, which means they need to have a smaller RMS squared velocity. So that one's opposite. This one's wrong. We just said they were going to be different. And the helium atoms have a higher RMS velocity than the xenon atoms. Okay, so that one's true for the same reason. Okay, so you're forcing some liquid through a tiny tube. So let's draw a tiny tube. By applying a pressure difference, delta P equals P naught. And the liquid flows out at a rate Q. So if you double both the radius and the length of the tube, what pressure difference do you need to apply to get the same flow rate? Okay, so it says here that we're using a tiny tube. So that should indicate that we probably need to use the tiny tube equation. So let's find the tiny tube equation. Here it is. Okay, so the tiny tube equation tells us that our flow rate Q is pi/8 times the pressure difference applied across the tube divided by the viscosity times the length of the tube times the radius of the tube to the 4th power. Okay, so if we're doubling the radius and we're doubling the length of the tube. Okay, so let's do this in two parts. This is the most clear-cut way I know to do these types of problems. So our original tube, let's call this Q1, has a flow rate equal to this, pi/8, delta P over eta L. So this is the first L. So this is L1. R to the 4th, and this is the first R. So it has a radius, little radius R1. So our second tube, I should have drawn it a little bit bigger. since its radius is bigger. So it has a radius R2 and it has a length L2. So the flow rate here is going to be Q2, 5/8, same pressure difference. Viscosity, the L has changed and the R has changed. So we want the same flow rate. So we want the flow rate for the first one to be equal to the flow rate for the second one. And we want to know what pressure difference we have to apply. So this should be delta P2 in order to get the same flow rate. So we want them to be equal. So we're just going to plug each of these in. So delta P, our initial delta P we called it P naught divided by eta L1 R1 to the fourth equals pi/8 P2, that's what we're trying to find, divided by eta L2 R2 to the fourth. So now this told us how the radius and the length were related. So L2 is twice as big as L1, and R2 is twice as big as R1. So this means we can substitute in for L1 and R2 to get our new pressure in terms of L1 and R1. So first of all, some of this stuff will cancel. So the pi/8 will cancel. The viscosity will cancel. So now we have this side, keep everything the same, P naught over L1, R1 to the fourth equals P2. L2 is 2L1. And R2 is 2R1. I need to raise that to the fourth power. So now L1 cancels, and R1 to the fourth is going to cancel with R1 to the fourth. And then over here we're raising 2 to the 4, which is 16. So P naught, it's the only thing left on the left, is P2 over 2 times 16. And if we solve for P2, this is 8. So P2 is P naught over 8.